Okay, thank you, Nadia. I'm going to specialize a little bit in the follow-up of what Nadia said by talking about MixOptim, which is a tool for the evaluation and the optimization of an electrical mix on a territory. So this work is a collaboration between people participated into the works of the ANCRE, the National Alliance for the Coordination on Research on Energy. This ANCRE is a kind of think tank, if you wish, and this think tank felt the need for developing tools for analyzing not only mixes but also scenarios for the energetic transition. So the problem that we wanted to solve is the following. You have a territory. This territory may be a city, it may be a region, it may be a country, it may be a continent. We do not specify. On this territory you have sources of power, wind, solar, hydro, and so on, with a given power installed for each source in megawatts. This territory is not insulated electrically. It can exchange import by import and export with its neighbors. And the power that is effectively produced at time t is this multiplet of beta I in megawatt, which is smaller than the installed power, of course. We have a fluctuating demand, D, which depends on time, and this demand must be satisfied by the production for all sources. And the production for each source is a proportion, X is smaller than 1, and depends on time, of a proportion of the total installed power here. So the question we want to answer is how much does it cost, large meaning of cost, to satisfy this electrical demand. And this is a complicated problem a priori because the demand is fluctuating, the availability of the sources here is time dependent also. We have a very specific ranking for the order of solicitation of the sources, and this makes the problem nonlinear with many conditional probabilities and an a priori difficulty to determine average values. It is difficult to use an Excel file and proportionality rules to determine the cost here. And therefore, we did a thing that every physicist does when he knows the equation but he is unable to solve them. He does a Monte Carlo simulation. Yes, François?
Where does come from the nonlinear characteristics?
Mainly because we have a specific ranking order for the solicitation of the sources.
Because I do not see it in the equation. Everything seems linear in the equation.
No, of course.
It's because of the constraint.
Exactly. You have constraints on this. Yes, you will see. So the demand is highly variable. This is the time dependence of the demand. You have seen this already. In a Monte Carlo calculation, we translate this chronicle of demand into a probability law, and the demand is treated as a random variable with this probability law. This is the case of the French mix, you see, where the demand goes between 30,000 and to 100 gigawatts. Okay, so wind power is also fluctuating. This is translated into, again, the availability of the windmill fleets is treated also as a random variable, and this is the density probability law for this availability. Okay, so we have a specific ranking of the sources to solicit the sources. The sources that are mobilized first are solar and wind power, and they are called mandatory or in French fatal. I didn't say that they are fatal for the health of the mix, but they are called fatal. The term consacré in English is non-dispatchable. So I hate this word. So I prefer the word mandatory. They are put on the market whatever happens, okay, and in totality. All the available power is put on the grid. And to complement the production, to satisfy the mix, then to satisfy the demand, you mobilize, you solicit after this controllable or dispatchable sources with logic, which is a mixture of frequential logic. You mobilize first the slow sources and then the faster ones. An economical logic where you mobilize first the sources that are low variable cost first, and also a political logic. The fact that you mobilize solar and wind first also obeys to a political logic. It is doctrine. Okay, nothing obliges you a priori to mobilize these first. Okay. Mix-up team, in order to calculate cost, needs input data, and we split the cost for each source into a fixed component, which is proportional to the installed power, and a variable component here, which is proportional to the produced power at time t. Okay? So this cost depends on time, because beta depends on time. In the fixed cost, you have, for instance, the amortization of the investment. In the variable cost, for instance, you have the fuel cost. Okay. And we extracted from the literature splitting and values for this variable and fixed cost for the various sources. Here. But these are input data that can be changed, in fact. This is chosen by the user. We also calculate the CO2 produced by the mix. And again, we have the same formalism as for cost. We have a fixed cost, a fixed CO2 production, and a variable component for the CO2 production. The fixed component takes into account, in principle, the whole life cycle of the sources. Yes. Okay, so I do not insist. Import and exports are treated explicitly like other sources. They contribute respectively negatively and positively to the power and also financial balance of the territory. And in mix-up team, the price of the megawatt-hour in import-export is treated as a random variable, and the import-export is determined by a stock exchange mechanism. Okay. With the complication, namely that the sources, the availability of these sources is limited by the interconnection capacity of the territory. Okay, and of course we have now all the input data for the problem, and we can run the simulation, the Monte Carlo simulation, and derive and obtain output data, which are, for instance, the load factors of the sources, which are the average power produced by the source divided by the installed power. So I insist on this because this is a specificity of this software, that these load factors are calculated. In many other evaluation tools, these load factors are guessed or postulated. In fact, we calculate, mix-up team calculates 3 indicators: an economical one, which is the average value of the cost of satisfaction of the demand expressed in euro per megawatt hour, which is the average cost divided by the average demand. We also calculate a CO2 indicator with exactly the same mechanism, and also an indicator of security of supply of the territory, which is in fact something like the amount of power that you need to import to satisfy the demand, and also the probability of being unable to fulfill this demand.
Do you have the same for export? If you cannot export and you are overloaded?
Yes, this is taken into account. Yes. Okay, so the Monte Carlo method. Most of you are physicists, so familiar with the Monte Carlo method, so I do not insist. This tool has been validated against the French Mix 2012, so it is
Verification.
Yes, it is a refutable model. And, well, it fits rather well for the cost, for the CO2. Less so for the import and exports, because probably the mechanism of stock exchange that we use for the model is oversimplified. We observe, of course, that there is a mutual influence of the load factors. If you increase, for instance, in the French mix, the proportion, the amount of wind power, then you see the mobilization of the nuclear source decreasing, as Friedrich Wagner explained with his model the day before yesterday. We have validation of mix optimal against the load factors. Again, then you see it works. We have confirmation, of course, that the system is highly nonlinear, and that the cost of the mix strongly depends on the average demands, but depends non-linearly of the average demand. And you see here, this is the case of the French mix, that for very small values of the demand, then we have a dominance of the fixed cost that you have to pay anyway, even if the demand is low. So, important result, we are dominated by the fixed cost. There is an optimal sizing of the mix. If I define the mix sizing as the total installed power divided by the average demand, and you see that if you oversize the mix, then you are really dominated by the fixed cost. And if you undersize the mix, then you are also you go to more expensive value of the cost of the megawatt hour, because you have to solicit more frequently expensive sources. Okay, so I pass on this. We applied mix optim to see what was the cost of the closure of Fessenheim. We can go back. This is just a flash. I would like now to go back to another chapter of mix optim, namely how to say, what can we say about the intermittence management and flexibility of the sources? This problem, of course, becomes acute if we increase the proportion of variable renewable energies, if we increase the interconnection between the territory and its neighbors. So the questions we want to ask is the studied mix able to follow the imposed fluctuations? How much backup do we need? How much do we gain in increasing the fluctuation speed of controlled sources like coal, gas, or nuclear? How much do we need in energy storage? So, in order to answer these questions, we develop a small formalism. You have already seen this equation, where I shall write it down because I shall need it afterwards, after the slide has passed. So, you see. Stop already. Okay, so I don't. Okay. Thank you. So, this is the demand, which must be satisfied by, in fact, two types of sources. One type, which is the so-called mandatory, plus the contribution of the controlled sources. Okay? And in fact, we say that we undergo the fluctuation of the demand and also the fluctuation of these controlled sources, wind and sun. And therefore, we transform this equation by putting here on the left side all the imposed fluctuations imposed by the demand and by the mandatory sources. And these fluctuations here must be compensated for by the variations of the controlled sources. Okay? And we do a Fourier transform of this thing here to make a spectral analysis. This is a standard procedure in physics. And the idea is that these fluctuations here, the imposed fluctuation of this power, defined like this, have a spectrum like this. We expect to have peaks at the daily frequency, at the weekly frequency, maybe at the seasonal frequency or yearly frequency. Okay, and the idea is to compare finally this spectrum with the frequency and power domain accessible to the controlled sources, and if we are able to envelope this spectrum with the domain accessible to the control sources, we shall be okay. The mix will be able to follow up the load fluctuation, and in the opposite case, it will be unable to do so. We have fast sources, we have slow sources. The slowness of sources is defined by a cutoff frequency, which is the rapidity with which it is possible to vary the output power of these sources. For instance, in the nuclear case, we know that we are able to vary the nominal power by 2% in a minute. And this gives us a typical angular cutoff frequency of the order of 1 hour minus 1.
It's symmetric up and down?
No. It is not symmetric, you are right. So there are complications arising from the non-symmetrical behavior of the system. We didn't go into this detail. Okay, this is, for instance, an example of the Fourier transform of the demand. Not the total amount here, but only the demand, where you see nice peaks at the diurnal frequencies. Diurnal frequency is here. Semi-diurnal frequency peak is even higher than the diurnal one, simply because probably you switch on your grill bread at 8 o'clock in the morning, and you switch on your TV at 8 o'clock in the evening. So you have, and you also observe harmonics of these two frequencies at higher frequency. Okay, this is a frequency spectrum of wind production. You probably do not see it's very pale, but there are also semi-diurnal peaks, which probably correspond to the fact that windmills are located, for many of them, close to the coast, and you have thermal breezes, and you see them here. Okay. Anyway, we derive from this kind of formalism criteria for the ability of the mix to follow up the load, and this is a Fourier transform sign here. Of course, this criterion simply says that the spectrum of this left-hand side here must be enveloped by the frequency domain, power frequency domain, available to the controlled sources. And okay, I have no time to go into detail right now, but we derived from this this kind of graph, where you see, starting from the French mix 2012, we plotted in abscissa the nuclear power in gigawatt and the wind power in gigawatt again. The position of the French mix 2012 is here, and this line is the frontier between the mixes that are able to follow the fluctuations and the ones which are unable to follow the fluctuations. We are here, so we satisfy the request hands down, no problem. But if we respect the ordonnance of the good Dr. Holland, we shall increase the wind power and decrease the nuclear power, and therefore we shall go, the evolution will go this way, and this gives you a flavor of the amount of modification that we can afford without problems of follow-up fluctuations. Yes, it's quite small, surprisingly.
But he wants 32 in nuclear.
Yeah. So if we obey strictly to this ordinance, then we shall run into problems of follow-up fluctuations. And for instance, we have analyzed mixes derived from various scenarios, including, for instance, the scenario of ADEM 2030 here. This scenario is characterized by a large proportion of almost half of fluctuation and mandatory sources, and small amounts of controllable sources here. And I'm sorry to say that according to these criteria of mix optim, this mix is unable to follow up the load, the fluctuations of the load.
Far from the frontier.
No, it is not far from the frontier.
As I said,
I know you have engineers who have looked into this. I know this, but this is what our mix optim says. So we should have to discuss. Yes.
As I said, we don't have 46 gigawatts from wind power. We have 32 or 34.
That was published.
That was published. I didn't invent it.
That's not our mix.
Oh, you changed it.
Anyway, you are not very far from the border.
It's 10 gigawatt less from wind power.
Can you show their position on your chart?
I have not the graph. No.
But I mean, the following diagram seemed to show, you know. No, the previous picture.
We go to discussion.
No, the mix is entirely different. So,
Finish up.
yes, I finish up. So, by doing this kind of analysis, I came to the same conclusion as Alice said. In fact, that the main problem in for the follow-up is not the high frequency ability of the mix. It is the low frequency ability. And the main problem, for instance, if we have much wind in our mix, is the anticyclonic spell. You may have no wind at the scale of a continent during 1 or even 2 weeks. And if you are, if you are confronted with this problem with wind power. Okay, so low frequency is a problem. So I have a few considerations about storage, power storage, and the benefits of power storage. Basically, introducing storage capacity, of course, permits one to smooth the imposed fluctuation, to smooth this quantity. So I do not say that storage should be designed and sized to compensate for the fluctuation of wind, for instance, specifically, or to compensate for the fluctuation of the demand. No, it must be designed to compensate for the fluctuation of this quantity. Okay? This spectral analysis here that I showed you previously enables one to determine what is the needed energy to be destored or stored to smooth these fluctuations at a given frequency. The higher energy you have, the destorable or storable energy you have, the lower in frequency you can smooth. Okay? So this is the formalisms. I have no time to describe it in detail, but you can read from this graph where you have we have calculated the Fourier transform divided by the angular frequency. You can read on this graph the energy needed to smooth the fluctuations at, for instance, the daily frequency. In the case of France, you need 20 gigawatt hour, which can be produced, in fact, by the pumping station that we have already. Yes. So, third part of the talk, but very, very short. Mix optim, as its name indicates, is also a routine which is able to optimize a mix. for instance, by means of a simulated annealing algorithm. We obtain from this optimization. By optimization, I mean that we vary the proportion, the power installed in the different sources, and we calculate the indicators, and we optimize with a multi-criterion of optimization. We optimize the mix. So 3 criteria: economy, CO2, and security of supply. Of course, these criteria are mutually incompatible. And so we get a Pareto front, this is an image of this Pareto front, a projection. We can also optimize on a unique criteria if we agree on the respective weight of the economical, environmental, and the independence of supply criteria, to make a linear combination of both, run an optimization, and for instance, optimize the nuclear power. And the optimization shows that if we weigh one-third, one-third, one-third the criteria, then the optimum for the French mix lies with an increase of nuclear power, not a decrease. Of course, you can choose the weighing coefficients. If you are at Sauvons-le-Climat, you will put certainly a larger coefficient here, and you will get another conclusion, of course.
Did you calculate the trade-offs by varying?
Pardon me?
The trade-offs.
The trade-offs?
Yeah, by varying the coefficients.
No, I didn't do that, but yes. So wind power can also be optimized in this way, so according to economical criteria, security of supply, and so on. And the global criterion degrades. The criterion, when it increases with respect to 1, which is the normalized criterion for the present French mix 2012, then it degrades with the introduction of wind power. But not very much. The Gen 3 nuclear power, the criterion is almost flat. So it gives you the amount of EPR reactors that might be built in France to optimize the mix. It's quite flat. Maybe a few EPRs, but it depends so much on the choice of the criteria that no real conclusion can be drawn from this. Okay, a few messages. The optimal mix has an installed capacity which is much larger than the average demand. So, message is, do not undersize the installed capacity. Another message, the optimal mix keeps much Gen 2 nuclear power in it, and we are far from the requirements from the government. This optimal mix is strongly export-oriented. We export some power in France, and it is valuable to invest in power production if you can produce it cheap, and if the interconnection capacity allows exportation. So I would strongly advocate the increase of the interconnection capacity. So we agree with our German friends on this point, probably for different reasons. Because in fact, Gen 2 nuclear power produces megawatt at a cost smaller than the average export price, and therefore closing the nuclear plants, the Gen 2 nuclear plants in France, would reduce this income source. In an economic crisis context, that would be a pity, probably. So MixOptim is an open software. It includes several modules: spectral analysis, optimization. We even have a module of genetic algorithm optimization, if you wish. It includes databases for the cost and CO2. And work is in progress. It is a recent software. We want it to be a completely open access software. So for anyone on request, I can give you the address where you can find it and run it. And on request, I can also give you the source code. And you are welcome to modify it and use it as you want. Its main added value is to provide a more or less correct treatment of intermittence with determination of the load factor and determination of quantitative criteria for assessing the fluctuation follow-up capability of one given mix. Okay, we are analyzing the Ancre scenario with it, not only the Ancre, but also the ADEM scenario. I promise to correct the install power wind value and possibly change the conclusion, I don't know. It is a validated software, at least on the French mix. We want to validate it on other European mixes, and Friedrich Wagner volunteered to give some value for the German mix in order to consolidate the software. Thank you for your attention.